morning. And first of all, I would like to thank the organizers for inviting me here. And initially, I decided that I will give talk only on nanobrain. And after coming here, I found that several people are interested in microtubule and related research. So I thought that I will divide my talk into two parts. And first 10 minutes, I will go for microtubule. But it will be a very brief introduction and summary of the microtubule research that we have carried out in our group. And then in the rest of the time, I will try to give brief overview of the research on nanobrain and related computing, natural kind of computing we are working on. So it has nothing to do with quantum entanglement, and it's all about coherence only. So phase and frequency locked synchrony and associated coherence. So those who think of quantum superposition and other things, I mean, it's not the issue here. So just to give a brief overview what kind of work we have been doing in my group in Japan, Tsukuba. So we designed molecule to realize molecular neuron and natural computing which works beyond Turing. Of course, quantum computer will also be beyond Turing or trans-Turing systems. So you all work on the different kind of computational principles based on natural computing, and we try to create a 3D system. It's nanobrain, which will be a little bit of prime focus today. And then we work on microtubule. Using molecular neuron, we try to grow cellular automaton circuit and try to realize computing on that surface. Then neural network, we just consider each molecule as neuron and we put them on the surface and try to realize the evolutionary logic and other kind of computing. And swarm intelligence. Swarms you can see as ants or flock of birds or school of fish, and they also develop intelligence not locally but globally altogether. So that's also kind of intelligence that is being used. So we use molecules to do that. So this is just overview of entire project that we carry on. But today I will talk for a few minutes on microtubule, then for some on nanobrain. So before I was just thinking how I can put these two topics together. Then I thought that it would be nice if I start from the brain. So if you think of our brain, it's a 100 GB storage device and a millisecond switch, but it can perform wonderful things, extremely beautiful things. And many of us carrying with us computers which are extremely more powerful. I have 1 TB say hard drive and 16 GB RAM, and with switching speed of nanosecond, so extremely fast, but still we cannot perform several things. And if we look at our brain architecture, so we will be surprised to know that we process only 200 MB data, but most of the resources we use to find out the communication rules and how to process the resource management of those data or those bits is more importance to us or to our brain like processors than storing large amount of information. Why is it so? When we devise new kind of computing or new kind of computing architecture, we hardly think about it. I mean, we always try to make faster speed, faster and faster. For an example, quantum computing and others. We try to put more resources, more memory, but that is not the case. In case of brain, if we look at it, the evolution process for millions of years, we will find that nature has concentrated on a completely different aspect, on the issue of resource management rather than increasing the resource as is. For an example, this was a very primitive brain, and let us see the transition of it, and we will find that the smaller part, that the brain there, even 65 million years ago, dinosaur had the similar kind of brain, and it grown, and what part has grown? If we look at it, we will see that the outer surface and most of the part that we have the brain here, it has folded. It is its size, if we just unfold it, it is equal to sum of 4 football ground. So it will be so big, and we have put it all together inside this skull. If we go through this on this surface, then we will find small columns, and you have neural network architectures there. In a few minutes, I will tell you a brief overview of how brain is operating, which is where the consensus has been reached. Of course, brain modeling is an extremely debatable topic. So we have this kind of columns where in a synchronized manner, the neurons are pulsating. There is synchrony and desynchrony or asynchrony also. So I don't want to get into hardcore computational terms to explain how the brain operates, but you can think that during the evolution process, this kind of increase in size was there. But the portion of the brain that we have just in the frontal lobe, those region works nothing, just resource management. And that part during the evolution process of the species, that part gave human an advantage by hardware architecture. So this is just a brief overview of the brain. And what is the operational mechanism? Let's see it. So first, I will concentrate on the smaller or the lower brain, just on the back of our spinal cord where it goes, and from that junction, the entire brain starts. So if you just look at it, so signal enters into brain, and it all passes through that the pons where we have hippocampus and that region, and then it moves to different section of the brain, and it acquires different path. If the connection is broken, then we develop different kind of disease. But whatever happens, there is one-to-many and many-to-one communication between different parts of the brain. So if we enter into the hippocampus, we will find a very typical architecture. It's like a spiral ring. It's a spiral architecture, and you will find that pulses, whatever the information is coming out from all over our body, it passes through these spiral structures, and this region is sufficient for the basic information processing, because many of the living species are living with it. So information passes through this, and if we want to detect it, then this region is sufficient. So what happens here? It's just a spiral ring. So sound, light, or shape, all information goes through this, and then something happens here, and after that it goes to the different part of the brain. So there is called short-term memory and long-term memory. So a couple of hours it remains in this hippocampal region, and it is sent to it is divided into different parts and sent to the different part of the brain, and it goes there. So from this region, communication occurs in a multi-channel way throughout the region. Suppose we want to detect an apple, then color of the apple, shape of the apple, and its 3D features are located at different regions, and then those regions, they interact with themselves in an asynchronous manner in the beginning, but as soon as the synchrony is reached in a nonlinear time duration, as soon as initially in asynchronous manner, and as soon as the synchrony is reached, and at that point of time, we just say that this is an apple. So this is how the basic brain architecture we know about. So there is synchrony, and there is some oscillation, some frequency, and something is there. So with this very crude idea, we begin. We begin with understanding neuron, because it should work as an oscillator if it really at all want to reach synchrony, and they have to vibrate in a particular phase and frequency, and phase and frequency has to get locked. So we took out microtubule, single microtubule from the brain, and we studied its electronic properties at the nanoscale. So you can see here, and this is a single nanowire, and we put four probe system. So remarkably, we found that all the electronic properties, even if you change the length of the microtubule, all the electronic properties remain constant. No property changes. Power dissipation, if you inject higher and higher current, the fall in the resistance, current voltage characteristics, all are identical, except one property, that is the resonance frequency. This resonance frequency, which one to select and which one to reject out of 8, that is determined by the length. Except that, no single property of the microtubule changes. So only oscillator is the key. And another thing is that every resonance frequency is associated with a particular phase, either 0, 0, same phase, 45 degree, 90 degree, 135 degree and 180 degree. So, multiple of pi by 4. So, that means phase, if you select a particular frequency, then phase, and if two signal comes at a different time to the hypothalamus, then the delay. So, phase, frequency, delay are the basic 3 parameters which varies with the structure. So, when the signal comes at a different time, we get time delay and we travel different distance and different things happen. So, same this result, particular result, I hope it will be published. It is in press in Nature Materials. So, within 2 months, I hope you will be able, 2 or 3 months, I hope you will be able to see it. The implication of this result is manifold. First of all, you can explain, you can think of dynamic instability, that 50 trillion cells of our body, we have microtubules and continuously length is changing, increasing and decreasing. Why? What kind of information processing is doing? So, first we have to understand a single cell. So, dynamic instability we can explain from here what is going on, and also several things. In case of hippocampus, we can understand how the information is realized, and we can shed significant light to the LTP and STP, that long-term potentiation and short-term potentiation. So, current theory, yesterday several speakers, they were talking about this gap junction beyond communication. I would just like to remind, that is why I kept this slide specifically to make a comment, make a very strong comment, that whenever you are commenting that this information processing, currently LTP and STP origin is assigned in this particular junction, and it is said that molecules, neurotransmitters are responsible for this communication, and this is considered as the switching region in the brain, and all theories are explained based on this particular assumption. So, whenever you are challenging, you are saying that there exists a synchronous communication, you are basically challenging the 80-year-old myth or faith, and you need to break that down. We should always remember, when we are trying to break one principle that is existing very firmly in the scientific arena. And if we say that we need, so one argument that I keep, that multiple synapses of a single neuron operates distinctly. Who programs them? Programming cannot happen here. Programming has to happen here, that which junction will operate, which will not, how will they operate, and etc. This is a simple common sense argument, but there are recently some Nature Neuroscience review and other review has come up, which is challenging this particular, but it will take time, and it will take a huge amount of scientific effort to break down this idea that memory in the brain is stored in the synaptic junction, and it is not in the synaptic junction, it is inside the microtubule, inside the neuron and inside the microtubule. So, our paper is a first and primitive attempt in this direction. So, whenever some of you are arguing strongly against this gap junction and in favor of synchrony, then we have to, everyone should be a little bit more careful. So, another thing I would like to say, that protein, we have considered these loops as, we have counted the number of loops and considered it as a circuit. This kind of rings as if inductors, and those redox groups in the protein as capacitors, and we have created a circuit, and we find a mirror like circuit here, and we calculate the resonance frequency, and we could match it very well with the resonance frequency of the structure. So, we feel that this kind of simple modeling would help, and we have also detected the solitons and other phonon and electronic solitons propagating through microtubule, which has the velocity of 450 kilometers per hour, and the signal processing speed in the brain is also around 400 to 500 kilometers per hour. So, we feel that microtubule could shed light on the speed of the brain communication process that is going on. And finally, before I end the microtubule part, so we have seen 8 different frequencies, and we try to measure quantum interference patterns on single microtubule, and we have got the superposition and particular symmetries associated with particular resonance frequency. So we don't know how they overlap, because in normal conventional carbon nanotube or other nanoelectromechanical oscillators which are found, which are created by us artificially, they have only one resonance frequency, and that's why quantum mechanically modeling them is very easy. But in the microtubule, what happens is that we have an octave band, and we see the complex pattern creation, which is not easy to model. We are still trying out, but I think it will shed some significant light on the quantum behavior of this microtubule. And also in future direction, we are going through bundle of neurons, bundle of microtubule, bundle 1 in neuron 1 and neuron 2, how they resonantly communicate, so that a global communication in the brain, entire brain, is understood. But this experiment was first done in 1988. They took one neuron at a far distance with another neuron, and they triggered with AC signal one neuron, and second neuron started oscillating in the same frequency. So we are now doing it at a bundle of with a bundle of microtubule, and trying to understand whether we can establish synchronized based computing as the sole phenomenon in the brain operation, so that we can decrease the number of brain modeling theories, because currently there are, I mean, enormous number of theories how brain operates, how information processing is being done. Mostly the basic global features is understood, but not completely. Now I would like to switch in the next, I would like to brief about if we try to replicate and try to create an artificial machine with the principles that we learn globally, and we have a convergence on knowledge on those principles, use those principles and then to try to build some artificial systems, then can we do it? So the target will be that, you know, information explosion is there. So we are continuously increasing large amount of information, we are continuously creating it, and they are getting entangled. So so if we want to process that information, how do we go towards it? And for robotics, the biggest problem is that many of the if-then statements has to be performed simultaneously. Of course, if quantum computers come, then it will be the perfect solution, because if you have millions and millions of if-then statements put together, then they can solve the problem instantly, of course. But there are something which quantum computation does not address. So we will compromise with the speed. We are not saying entanglement, but we are saying coherence. Okay? So it is in between classical and quantum. So it is like quantum-like, you can say. So it's phase and frequency locked. That means if you look at it from outside, the two signals propagating, their phase and the frequency is the same. But if you change one, the other may not change. Okay? So the superposition principle in the, as it is written in the quantum textbook may not be valid in this case. So we want to use it for medical purpose and other kind of thing. Okay, so principle is that we will have a central control here, one-to-many communication with the environment. Now forget about the very, very complex brain. Now we want to create something very simple, very, very simple in the lab, and we want to understand its potential, and we want to verify whatever we learn from the brain in a very simple device. So in our computational model, what is new about it? First is we consider cellular automaton. Those who doesn't know what cellular automaton is, I'm going to explain it in brief very soon. So in cellular automaton, you consider entire world, entire universe as composed of discrete cells, bits. It's like a checkerboard, and you have change in color of the checkerboard, and that gives you the computing. So it came in the 1960s. It's a very old concept. What new we have introduced is that it has many different layers, and higher level computation goes on, and it depends on the lower layer. Unique fusion of Boronoid decomposition and cellular automaton. So different part of the brain, they communicate and they reach synchronicity. And how can it happen? So we can divide the entire computing surface, the checkerboards, in many different regions of Boronoid decomposition, and we would like to synchronize them. And we use multi-level cell, that is beyond binary system. Again, as other every speakers did, I am also quoting from Feynman. Okay, but this quotation I don't think anybody said. Nature had some extremely microscopic scale operates exactly like discrete computer logic. So I have often made a hypothesis that ultimately physics will not require a mathematical statement, that in the end the machinery will be revealed and laws will turn out to be simple like the checkerboard with all its apparent complexities. The Character of Physical Law is a book by Feynman, and it's a very interesting book where he argues that if truly the many-body theorem has to be addressed, it's a different topic though. If you really wanted to have many-body theorem, the simultaneity when it comes, you cannot write down in terms of an equation. Instead of that, you need some checkerboard-like system where you have discrete color of the states, and that pattern will explain the physical phenomenon, not the complex equations the way you put forth. So that's the inspiration. And just to tell you some intractable problems. So computer scientists always look for the problems which is not possible to solve. And one of the problem is like CAPTCHA, where you have twisted the letters. So you can read it very easily, but computer cannot in finite time. Of course, if quantum computers come, then they will instantly do it. But there are some situations in which quantum computer cannot operate. We can penetrate there. And algorithm is not known. Where algorithm is not known, you need to learn and you need to develop some sense. For an example, differentiating between Korean, Chinese and Japanese. How do you do it? So sitting in India, everybody would look same. But since I'm in Japan, I can tell who is Japanese, who is Korean and who is Chinese. But if you ask me what are the laws, what are the arguments that I have used, I cannot tell. It is something similar when you are talking to, when your wife gets a little bit annoyed and there is a very subtle expression in her face, you can easily make out that what is going on in her mind, and you cannot tell argument-wise how it is happening. So this is kind of intractable problem. These are set of intractable problems where algorithm is not known. Algorithm you cannot write. Through learning, you build it, and that algorithm works in computing. And in this case, algorithm is known. You know how to find it, but only time takes a very, very long. So in case of CAPTCHA and others. So if you calculate, the time is very, very large. So that's why quantum computers, which is based on the logic gates and other things. So you can really put it down and you can really try to solve it. So only thing is that, for an example, traveling salesman problem. So traveling salesman problem is a very famous problem. It says that you have 20 chairs, and if you are asked to go to the first chair to second chair to third chair, and come back to the first chair, then you can do it very easily by choosing minimum distance path. But if computer is asked, computer will check all the possibilities, and then it will decide which one is the minimum, and then it will go. So approximate solution making algorithm is not a prerogative of the computer. So it will take long time. So depending on the intractable problems, the time goes on number of elements you want to solve. In case of nanobrain or synchronized computer or our normal brains, it goes linearly, because I don't want to get into details, but it does not goes n to the power square or n to the power cube or factorial n, simply because nonlinear synchrony, there is something called in synchronous system, there is some term called nonlinear frequency pooling. So that's something like if you take say 20 oscillators and try to synchronize, the time it will take. If you want to synchronize say 40,000 oscillators, and if you want to synchronize say 100,000 or 500,000 oscillators, all are coupled together, the time will not increase exponentially, it will increase just linearly, and it's a very small time increase. So we have shown in the microtubule research that the time for collapse of 200 oscillators in our living cell, in the room temperature, in open condition, the time taken is 1 microsecond, and when we collapse 40,000 oscillators, then also it is nearly 1 microsecond. So maybe some nanosecond difference, but time nearly remains the same. Even in case of coupled oscillators, if there is a positive feedback that is working in it, so nonlinear frequency pooling is something that allows the entire chaotic system to collapse into a single phase and frequency locked state extremely fast. So that's why That's why this is the advantage. But if it is a quantum computer, where the line will be, the x-axis completely. So it's not, it's instantaneous. So that's the difference. So we compromise with here. Okay, so just to introduce you, we are not the only one group in the world who are working in this kind of natural computing. Natural computing is a very well established research field. This is one work from Japan, and this maze problem is one kind of intractable problem. It's very hard to solve, and this is an algae, and the food is there, and it finds the food and it solves the maze problem. And this was published in 2010 Science, and these are the small salts, and these are the algae we have kept, and these are located at particular position of the Tokyo suburbs, and these algae connects these salts in the same way as the minimum distance path, and it solves the problem, this intractable problem. So it was a huge news, and it is now one of the most funded. So this intractable if you want to solve this problem by computer, it will take more than the age of this universe. Still you cannot solve, but it does it in a few hours. So Japanese government invested 600 billion Japanese yen, huge amount of money, just to build up this kind of computer for a larger scale. So these are called natural computing, in which we allow the natural properties of the system to work and to go through and to solve the problem, to search and find. So it is different from what quantum computer people wanted to do. They want to increase the speed to a Mammothian level, I mean incredible level where you can't reach. But here we are not concerned of the speed. We are concerned about some complexity of the system, and we want to include this complexity inside the computing paradigm. So there are 5 or 6 different groups all over the world who are trying to do this. For an example, in UK, Andy Adamasky is trying to do it on a water beaker. He puts some chemicals, and they arrange themselves like the reaction diffusion system, and he's trying to solve intractable problems with that one. So all these researches are, I mean, does not require much funding. I mean, why are they being funded for billions of dollars? I don't know. But in any case, these kind of concepts has potential not in terms of speed, but in terms of arguments, creativity, and intelligence of the system. So their prime focus is completely different. Okay. One thing I would say that parallelism is not simultaneity. I hope, since this is a conference of computer science, I hope that everybody understands this, because when you divide a work into multiple different channels and then you add up all the works, that is parallelism. And when simultaneity, it means that they will interact with each other in between themselves. So in parallelism, you don't keep it. So it's a very fundamental principle of computing, and I hope everybody knows. So I just skip. So Turing machine, I think also everybody knows. So we have a machine, registering machine, and we have a tape. So any information in the world we can translate in the form of 101010, and we just have a registering machine. We just make a hole on the tape, but the length of the tape will be infinite. So this 1937 philosophical principle is extremely strong. But both quantum computer and the synchrony based computer that we are proposing, or natural computing, whatever we are proposing, we want to break this. So everybody wants to break this concept. And how they want to do that? The principle is very simple. So the Turing machine will go in this way, but simultaneously we will process some other bits also in this direction. But for quantum computer, it is just one line. So you just simultaneously in this line, you finish it up. So irrespective of the huge bandwidth that you have. But for us, as we said, that we compromise with time. So all the natural computing people who try to explore this path, they go like this. They do some simultaneous processing, and then sometimes sequential, sometimes again some parallel, and then sequential. So it's a composition between the two. So that's how this 3 triangle is formed. One is the Turing type, von Neumann, where we have single tape, and then quantum, where on the tape you have just one bit, because simultaneity is so large, it consists of entire system. So it just collapses. That gives you. So it's just a point. And then another part of the triangle is like ours, where we have simultaneity and then sequentiality. It's in between quantum and something, because we don't have any entanglement. Okay, how do you want to do it in our lab? So one-to-many communication at a time. So that we will do. We will try to realize correlating computing constructs with the physical parameters of a system. So so one thing you should know that all these people who try to realize natural computing, they never talk about logic gate. So we don't talk about logic gate. It's a pattern-based computing. So input is pattern, output is pattern, and in between we find out some correlation rules. So correlation rules, in our case, it is cellular automaton and Boronoid decomposition that we think is the most easiest way to practically realize. And we trigger synchrony through nonlinear frequency pooling to convert choices. So we make the switches such that they will oscillate like neuron and they will converge. So we just try to replicate the way brain is operating. Interpret dynamics or output with the result. Repeat this with as many systems as possible. And then this is a complete overview of the thing. So what is cellular automaton? If some of them you don't know. Cellular automaton has 3 rules. Cells update at a time. Cells follow local rules independently. Rules are homogeneous. So that means if I have a checkerboard like this, these are cells. Now these cells can change color black and white. So if it is a black, it can change depending on its neighborhood. But if A is changing, B can also change depending on its neighborhood. No problem at all. So rules are homogeneous everywhere, and local rules, they operate independently and simultaneously or in a sequential manner they can update. And what are the rules? Rules are like this. Suppose you have a black dot and you want to find the next one. So next one is black, black, white. In this way, we write the next state of this black. And if we want to evolve a pattern, suppose I have a grid like this and this black state. So you will start like this. This green one, white, white, white. So next state will be white. Next state for this white, 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 black. So rule 7. Then white, black, white. So we get white. And then black, white, white. So we get black. And then white, 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 we get white, and so on. Apparently, it may turn to you as a very simple process, just a kid's game, but you can create enormous complexity just with this simple process. So several people are trying to prove, and some people have taken DNA-based structures and solved some intractable problems in finite time. Because if you can encode some intractable problems in this way and take DNA molecules and put it in a water beaker, then after a finite time, the entire growth will be there and the solutions will be ready before you. So I don't work in that process, but there are some groups who has published very highly reputed papers on this. So complexity could grow enormously. So this is the CA I showed. And if you change the rule, you can change it and you can create significant amount of complexity just with this. Just to give you some examples, so you can encode, you can write it in a software program, so it grows. So it took nearly 20 years for Wolfram to do this, because computer get hang after a few states, because it expand and expand. So if similar kind of thing or like fractals, if this kind of situations occur, with simple systems you can realize it. You can experiment it in your laboratory with some set of molecules, and you can see that enormous complexity that you can generate. Okay, trees I will leave because of time constraint. So we choose molecule. So we choose molecule and try to make grids like this. We try to encode bits and try to see pattern evolution like the cellular automaton. So the molecule has 4 states. And it accepts electron and donates electron to do that. and we create different communication circuits, and that those circuits can evolve. So I would like to get some time just to show you different circuits, just a few examples of that. So these are the scanning tunneling microscope image, the STM, the tunneling current image of the molecules, and molecules are changing their path. So these are the basically quantum tunneling through the molecule, and these things are local density of states. So this is the probability density wave of electron moving from one molecule to another molecule. It is not there is something. So probability density of electron moving here to here could be imaged directly by scanning tunneling microscope. So that's what we call circuit, and this circuit evolves. It's like the evolving circuit that we created. So if you want to read the details, you can go through our Nature Physics paper last year, and we have detailed the things there. So what we do is, this is a scanning tunneling microscope image. These are up ones are molecules. They are up means higher state, blue means lower. So green, blue, this kind of different color we assign, and we check the pattern evolution. Then we ask the computer scientists to interpret those images and find out the cellular automaton rules. And I don't think my student is here, so they built, so every year I invite students from IITs who develop some of the things. This software is built by Rishi Bhartiya from IIT Kanpur, and this is a program where if you encode any of the patterns, STM images, series of STM images, it will directly tell you the cellular automaton rule. So it's a fantastic thing. So now just to give you a brief overview how the computing is done, let's look at this video. So as you understood the cellular automaton, we should have a grid, and we should have a initially blue ball, and we give electron or take out electron. If we give one electron, blue becomes green, and give two electron, then blue becomes red. And if we can also, if we withdraw electrons, it becomes yellow. So in this way, 4 states could be written. Now we go on writing these states on over the surface. This is a ultra high vacuum scanning tunneling microscope system based system. Now they start changing their pattern by themselves. You can resemble it with the neurons flashing continuously in the brain. So the complex, so we put gold layer in actual reality, and this kind of balls are replaced with molecules. Okay, so we get the entire 2D grid, 30 nanometer by 30 nanometer, or 100 nanometer by 100 nanometer, or even the micrometer scale. So after that, if you really scan the surface, this is the actual image you see. That was the schematic. Now if you look at the real picture of the tunneling image, then you look like this. And after that, you start writing the pattern. You can give an input pattern, it will give you the output pattern. And what kind of problem you want to solve, based on that you create a statistical database, and you give those inputs, and then you can give the boundary conditions and others. You can solve differential equations. So we have solved several differential equations with this process, and some of them is also included in the Nature Physics paper. You can go through, and in the supporting online material we have given enough details how to do computing with this. The one beautiful thing is that if you write an input pattern, say like a triangle, like parallel lines and something in many different ways, but you cannot make it full. Every time it will tell you that you have written a triangle or a circle or something. We have checked the possibilities of theoretical possibilities of when can we break it. So we, in principle, 10 to the power 44 different kind of triangle you can draw on this surface, and still it will be able to tell you that it is really a triangle. So biggest problem in the computer science is that if you have a cat and a dog, and if you ask a computer to identify a cat and differentiate between a cat and a dog, it can't do it, because it can do only those pictures which has been encoded into it, which has been programmed into it. But if it is something new, it cannot algorithm. But if it is in the embedded dynamic behavior of the system, then it can. In this way, 10 to the power 44 different triangles it could detect. That means when you try to encode, so depending on the differential equation, pattern changes. For an example, couple differential equation, you should put ring. If two couples, then 2 rings, 3 couples, 3 rings, and depending on the radius, you change. So boundary conditions, these are very technical nitty-gritty terms which you need to keep in mind if you want to use it, because you cannot go for longer terms. So in this way, the number of states come, and you need to assign a state to the particular parameter if you want to do compute with it. And this surface, if you take out one molecule, after some time it reconfigures itself. So it heals itself. So it's just an energy minimization process which helps them to return to the same structure. So some of the large number of differential equations we could. So some of the intractable problems we have already shown in our publication, and 10 to the 44 differentials. So 2 different classes of problems we have shown, because if you show only one classes of problems, then people will argue there are many similar kind of computers which has been built which can solve only one kind of problem. They are not universal. So by arguing universal computing, everybody will refute you. So we solved 2 different kind of equations. Of course, if somebody says that, look, you can solve only 2 different kind of problem, not 3 different kind of problem, the logic is already there. I'm not ruling it out. But the problem is that we are at least one step ahead of the conventional system. That's what I want to claim. And it learns with practice. 10 to the power 4 different choices of triangle straight lines can be detected in 3 to 6 to 9. That was the time. That is the normal time of the other groups also. Those who are working on a completely different system and trying to solve intractable problems, they also solve it in 9 to 10 minutes or couple of hours. What is different for us is that we can use it several times. For an example, most of the papers that you will see, most of the computing that is addressed in trying to address intractable problems, once the computation is done, you need to throw out the material. But on this surface, you can rescan and you reuse it. Boronoid decomposition, now I will go. And in Boronoid decomposition, you divide a space into 2 parts, so that distance from this point to this point and this point to this point is equal. Okay? And if you put another point, this point to this point, and distance between these two, distance between these two is same. In this way, you divide the surface into many different structures. So using Boronoid decomposition, you can create many different structures, and in nature you can see Boronoid decomposition in several places, and we use it to encode intractable problems. I don't have time, so I'm just skipping the things. So you could realize these kind of circuits, multiple different circuits on the surface, and we could converge them by triggering, and we could regenerate the MRI image. This is just for fun. And so time does not increase exponentially, it increases linearly with the complexity of the problem. Address multi-level communication with different parameters at a time. Explore astronomically large choices. So in couple of cases, in 4 cases we have shown. I mean, don't consider this kind of computers as universal computer. You can encode anything and you get the answer. No. So 4 different kind of problems for which you cannot make it full. So normally, if you ask me anything, any pattern for many different things, if you train me that this is a triangle, this is a flower, this is something, I will learn it and I can solve it. So it's almost like an universal computer, my brain. So we are not at this, we are very, very primitive. So only 4 cases, 4 problems: triangle, rectangle, a triangle, square, circle, and these kind of patterns. If you write four different parallel lines, then you cannot make it full. So this is something like this. When we published this, there was severe criticism that we are doing it in ultra high vacuum and in a big STM chamber that is not a computer. And showing this kind of thing, molecular electronics people try to create a lot of noise and other things. How can you ever practically realize this? And common people can never use it. It cannot have any practical application in the future because of huge scanning tunneling microscopes. So if you go through our news coverage all over the world, all press, news, I mean, all of them, almost all of them criticized. We said that, look, it is room temperature, quantum computing is not in room temperature, who cares, this is a big machine. Okay, so after listening to this, I thought that we have to make some changes. So I then invited some chemists as postdoc to my group to work with me. I started designing and started thinking all around it in a completely different scale. Okay, so the first thing that I would like to say is that many people are aware about molecular machines, and you see beautiful videos like this. For the last 20 years, people are showing these videos and publishing Nature and Science one after another. This is inside near the heart, and these are red blood corpuscles. So as heart is pumping, so you have some cholesterol there, and molecular machine is coming and then getting up the fat parts, and they are going. So like this, many molecular machines paper has been published, and people are claiming to change the world with this kind of machines. One thing they always missed, and from 2004 I am continuously arguing that these are funny video, nothing else. Just because at the nanoscale, if you just think clearly in your mind that what number of decisions these machines have to take, several instant solutions you need to take from the sensors, you need to process it, and at the same time you need to give decisions. We are unable to send a mission to Mars for 0.3 degree angle deviation. The entire mission just collapsed because the signal came, and signal reaching there, you just couldn't correct it. So even the Asimo robot, one of the best robots in the world, Asimo robot in Tokyo, you can test it. So if Asimo is walking through this, and this red carpet is little bit deeper than this color, then Asimo will be confused and stand there. So this is the level of human intelligence incorporated to the robots. The level of intelligence I'm talking about. So little bit change in the condition, input condition, then robot finishes. And how could you think of this kind of robots and machines will go there and take so many different decisions at a time? So you need a nano brain. So this is the reason why I argued for nano brain in 2004 and 2005 and started working on that. So I said that if you want to start towards this making this kind of brain-like machine or computing machine, first thing is you need to test one-to-many communication and many-to-one processing at a very atomic scale and try to understand it at a very basic level. So in 2008, this work is quite old. 2008, we built this system. So like one person can talk to many others. So we put one person, one molecule, and 16 molecules around it so that they can talk to each other. Okay, so this is the structure, and if you tweak with the STM tip with the central molecule, you can change the central 16 molecules in a logical way. So just let's see the scanning tunneling microscope. So this is a tunneling image, that is the tunneling current that is coming out, and you tweak with only the central molecule, and they change in a fairly logical manner. And we created a truth table of the system and tried to see versatility of the system, and 2.6 billion solution it could generate, and we could assess several of them, and we could create a truth table. So what was the conclusion from this is that if you trigger one-to-many and many-to-one, of course at the molecular orbital scale, when one molecule is coupled with other in the orbital domain, then it is possible for you to generate enormous amount of and encode enormous amount of complexity into that molecular architecture and molecular system. So inspired by this, we went on extending our research towards a larger architectures. So we wanted to make 3D. Soon we realized that if we go for 2D and want to make natural computing, it's impossible. Because if we want to go scale up the system, we are not able to do that. Defects come in and several things occur. So what if I have a center and I extend in 3-dimensional different directions? So what about that? So with this idea, we started to do. So same thing will happen. On the top we have cellular automaton, so it is 3D cellular automaton, the same cellular automaton I have said, but instead of those square boxes, you will have a cube. So you have a multi-level channel. So, and what would you read out? So it will be a standalone system in the solution. So nobody can claim that, okay, you are doing it in the USB STM anymore. And we will put laser or chemical composition in the solution, and then we will use laser to probe the system. So we can put different sensors, and we can detect what the things come up. Those who doesn't know CES, that is combined excitation emission spectroscopy, it is a spectroscopy in which you apply in the x-axis different laser excitation of wavelength, say 200 nanometers to 900 or 1400 or 1600 nanometers. And in the y-axis you have detection, say 200 to 1400 nanometers. And in the 2D plot, you will generate a map. It's a map of fluorescence which is coming out from which. So if there is a structural change, if there is a symmetrical change, if the switch is on and off and other things happen, everything will be mapped on that 2D surface. So reading that map and interpreting it, so if we get any kind of map or pattern that is evolving from the system, we can try to find out the cellular automaton rule and we can use it for computing, as I showed on the surface of the molecules. The same thing here. So I would like to show you how the CS spectra. These are the very simple examples of the initial nanoman structures that we created. So you get these are the Raman ridges. Forget about this, but you get very complex set of patterns when you grow the complexity of the systems. So you have wavelength here, excitation, and the emission is here, and you have different patterns. So with time and with different conditions, they change, and you interpret that in terms of cellular automaton and try to understand computing. So now these are some of the structures. I am not going to molecular machines in details. So the idea is that we have we go through rigorous theoretical simulation process. Which molecule should we choose? Which one give which color? And we always keep in mind this window effect, that blue should be outside, red should be inside, and several other parameters, redox activity, the switching state of the molecules, how do they interact, intermolecular layer energy exchange. So we have multi-level switches here, and the communication goes through multi-channel this. And these are the molecular machines that we designed and grow. So my molecular machines we test separately with scanning tunneling microscope. How do they work and how do they behave? And we create the entire 3D system, and then we test it in the solution. So of course the first design didn't work and second design didn't work, but slowly we started optimizing the thing, and we tried to find out a logical system or logical behavior. Some of the things that we have been succeeded, I would just like to summarize. So how do we grow these structures? So these are the small molecular ligand. So chemists synthesize these structures. They just put it together and they just create the dendritic one-to-many communication network. And this multi-level switches then we dope inside the molecular structures, and then we attach machines and sensors to it. So you know, one of the primary thing of natural computing or brain-line computing is that the decision making and processing or memory storage, everything is done at the same place. So in this way, we created several different structures, changed the machines, and depending on the sensors, we tried out different possibilities, and using that, our future direction would be growing even more and more complex structures and trying to understand. But at the basic scale, what are we saying is that here blue balls doesn't denote laser light. It's a very small system. It's a chemical system that you got. So if you activate a sensor, you expect that the signal transmit, and it goes to the central region. So every region it goes is a fluorescent bump. You see it in a CWS spectrum, and then it goes out and it activates the molecular machine. And as soon as it activates the molecular machine, again you see some fluorescence in the CWS spectrum. So this, if several of them get activated simultaneously and they work together, you can change the ion concentration in the solution. You can modify the pH concentration in the solution and the several different parameters, the way molecular machines normally being studied. And then every signatures that you get here where the light comes out, you see it in the CWS spectrum. So separate machines you just study, and then you combine together 1 by 1, 2 by 2, 3 by 3, and then you see. And you can visualize temporal behaviors also, that how it creates the pulses, the fluorescent pulses, and its periodicity and its temporal behaviors and all other features. And you can program them also by changing the molecular structures by different generations, by different other methods. Okay, so So one thing we wanted to do that we could not do possibly very well on the 2D surface is that we will practice the system with particular kind of condition time and again, and make some permanent conformational change and induce a particular symmetry in the molecular structure, so that when the fluorescence image comes out or next time, it learns it and it follows accordingly. So this kind of experiment is not the first time, it was done before, but on a different context. We just copied it and we just implement this. So just to have a look at it. So if you just practice it several times, you get permanent structural distortion and the generation of a particular symmetry. Let me tell you, the CWS spectrum is the most authentic way to understand if there is a structural symmetry takes place. For an example, if you have a graphene or if you have a carbon nanotube, you want to understand how the fluorescence behavior is getting changed. So in this way, 3 different disks are created, and once the disks are created, after that you will find the CWS spectra has gone significant changes, and particular wavelength of light, if you trigger at a particular say 560 nanometers, if you trigger, you will find that the interfluorescent behavior has been changed dramatically. So it is kind of going through a particular changes. Of course, there are a lot of ways to go, and the next experiment that we were trying to do with this structure is that if we make multiple different kind of learnings together, then whether it can change the entire signal processing process or not. So the same thing, we during the synthesis process we can make provision in the molecular structure, so that with multiple conditions, for an example pH, we can create multiple disks inside, and with say optical probing, optical pumping, we can create multiple disks inside. Then when we probe with a single light, we find that the spectroscopic behavior changed. Especially what we could create complex pulse behavior, fluorescence pulse that comes out from the system, and we could change its delay sequence. So a pulse with a delay and a pulse with a delay, and this kind of sequence we could generate from 20 nanosecond to 60 nanosecond delay. We could model it. So it is not at all in the time domain of the biological computers. In the time domain of the biological computers, it is completely in a different domain, but we are trying to realize some of the features that you are seeing with the normal systems. So I would like to thank my postdoc, Dr. Satyajit Sahu, who did most of the STM experiments, Dr. Subrata Ghosh, who did the synthetic and all other parts. He is basically leading, so they lead the work. I mean they take the decisions, and this is Krishna. He did the microtubule. You can see nano electromechanical systems. So entire interfacing and all other things in my laboratory is built by him. And I would like to thank all of you for listening to this.
Hi, Keith Heipel, University of Waterloo. Thank you for an excellent presentation. I don't know if I'm saying this correctly, but they're actually examining the brain itself, a physical system, and trying to figure out how it works. What ideas would you like them to investigate to help you further with the system design of your machine?
First of all, instead of entanglement, I mean, if coherence could be investigated further, because coherence without entanglement has several advantages. It is quantum. Of course, it is a quantum-like. I mean, you cannot differentiate between the two states when they are synchronized absolutely. You just can't tell that whether there is superposition or not, because you would not like to touch the system. But at the same time, you can allow the enormous amount of data to get input into the system without destroying the synchronous behavior of the system and regenerating and coming back to synchrony. So a feed-forward mechanism, I couldn't tell it in my talk. So a feed-forward mechanism is always activated in our system also. In the microtubule research also we have seen that, that a feed-forward mechanism is something like, suppose a system, if it's a purely nonlinear system, it's vibrating in this frequency, and then slowly it reaches to the synchronous level. So in the oscilloscope you can see that this kind of situation is going on. Now if you input some large amount of more signals with it, you will find that they oscillate, they take into account those signals and it still reaches synchrony after some time. But with quantum behaviors, you just You just dared to do this kind of experiment. You just dared to do this kind of thing. Just think about our brain. It is operating under noise which is more than the signal. It's more than the signal, but still it is able to operate. Why does it so? I mean, it's because it is altogether following a completely different kind of